Okay everyone, welcome to this week's tutorial. So this is week 9 and I'm away. So today we're going to do chapter 6 tutorial exercises. Chapter 6. Okay, and we're going to do question 1. 2 and 3 are essentially table looking questions. I will skip them and we'll do 4, 5 and 6. Okay, so question 1, we have x1 up to xn being independent normal random variables with mu being the mean and sigma squared being the variance. So the point is determine the distribution of the following. Right, so determine the distribution of the following. So let's do them one by one. Okay, firstly you have sum of xi, I is equal to 1 up to n. Okay, since these random variables x1 up to xn are independent and identically distributed, you see they all have the same mean and the same variance, we know by, say, convolution formula or linear transform normal that this is normal, but you sum up the mean, so this n mu, and you have to take the you sum up the variances also. So this is variance n sigma squared. Okay. Of course, if you like, you can always compute this. You can say compute the variance of sum xi I is equal to 1 up to n, and say here by independence you have the variance of the sum is equal to the sum of the variance, right? So you have variance of xi, which is equal to n sigma squared. So you, simply by doing that, you can deduce that this is true. Okay. Now, next, 2, we have the average. So x bar. Okay. Of course, since you know that the sum is normal, average is just 1 on n multiplied by the sum, right? You can simply, from this, you can deduce that, again, this is a linear transform of a normal, so you can deduce that the average is in fact normally distributed with mean mu and variance sigma squared on n, right? Since when you compute the variance of 1 on I is equal to 1 up to n xi, this is equal to n squared when you take out the constant from the variance operator, right? This is 1 up to n xi, and that we have computed before, which is n sigma squared, so you just have n sigma squared. Okay. I mean, how I know this is normal, I've used the fact that linear transform of normals is again normal, which I've studied in the lectures. Okay, so let's go on to the third one. Right, the third one we have x bar minus mu divided by sigma multiplied by square root n. Okay, and I'm just going to rewrite that, and from that you will quickly see what the distribution of this is. This is simply that, right? And from the previous question, we see that x bar is normal mu with variance sigma squared on n. Then this is a standard deviation, so this is simply standardizing the average. So this is normal 0, 1. Okay, so that's quite easy to see. Next, part 4, you have n x bar minus mu on sigma all squared. Okay, so just by looking at this, this is the square of the previous one, right? And from lectures, so since from lectures we know that if z is normal 0, 1, then z squared must be chi-square distributed with parameter 1. Okay, so this is why you're just squaring the previous result. Okay, so that we know this term here is chi-square 1 distributed. Okay. Next. Okay, and let's just move on to the next part. Part 5. Part 5 we have xi minus mu on sigma, but since you know xi is normally distributed with mean mu and variance sigma squared, then obviously this is just standardizing the normal. So this is normal 0, 1. Since xi is normal mu sigma squared. Okay. Next is the same as before. Obviously xi minus mu on sigma squared. You're squaring a normal 0, 1, so this of course has to be chi-square 1. Right. Now, the last one, 7, you're asked what is the distribution of the sum from I to n of xi minus mu on sigma all squared. Okay, so you see xi minus mu, so firstly xi minus mu on sigma we know is normal 0, 1, which tells me xi minus mu on sigma all squared is chi-square 1, and you are summing chi-square 1 random variables. Okay, now we've learned before that when you sum over independent chi-square 1 variables, you get back a chi-square random variable, except you change the parameter. So therefore, when you take the sum of 1 up to n of xi minus mu sigma squared, this follows chi-square n distribution. Okay, because you're summing over chi-square 1, and we'll show the result in class that when you sum over chi-square 1, you get chi-square n when each one of them are independent. Okay, so that's question 1. Question 2 and question 3 I will skip because they usually involve reading tables, and in my opinion, tables are somewhat obsolete. Okay, so if you're interested, of course, when I come back, you guys can ask me about how to do these questions. Okay.